Hello and welcome to CS Ninja. This new video series is on data structures and algorithms, and today's topic is trees. Unlike arrays, linked lists, stacks and queues, which are linear data structures, trees are hierarchical data structures. You can understand this hierarchy from a real life example. John is the CEO of a company. John has two direct reports, Steve and Bella. Steve has 3 direct reports and Bella has 2. This type of hierarchy can be represented by tree data structure perfectly. But this is not the only use of trees. We will learn more uses of this data structure in great detail, but before we must learn basic terminologies regarding trees. Here we have our root node. Root node is the topmost node of the tree, and if there is no root node, there is no tree. And then we have our leaf nodes. Leaf nodes do not have any children. They are at the end of the tree and they are also known as terminal nodes. Now let us consider A is a root node. And if A is not null, then B and C are considered as our subtrees. Now let us see what are ancestor nodes. Ancestor nodes are all the nodes above the node itself. What I mean to say here is that if somebody asks you what are the ancestor nodes of E, then the ancestor nodes of E are A and B. What are the ancestor nodes of G? Ancestor nodes of G are A and C. Now what are the ancestor nodes of C? C has only one ancestor node, and that is A. Next key point here to learn is what are levels. Just like in a building, we have a ground floor, a level 1, level 2 and so on. In trees also we have levels, but starting from the root node. Root node has a level 0 and the children of root node are designated with level 1 and their children are on level 2 and so on. In some books you may even find that a root node is starting at level 1. Now let us learn what are children. All the nodes below that specific node are its children. In this case, B and C are children of A. Similarly, D and E are children of B. In a similar fashion, we can define a new term which is known as parent. As we know that B and C are children of A, so we can say that A is parent of B and C. Similarly, we can say D and E have a common parent as B. Now it's time to define a new term, that is degree. Degree is nothing but the number of children a node is having. So in this case, A is having 2 children, hence its degree is 2. Similarly, B and C are also having degree as 2. But the leaf nodes are having a degree 0 since they do not have any children. Hence D, E, F and G will have a degree of 0. Now let us see what is an edge. Edge is nothing but a connection between two nodes. So all these connections you are seeing in this example are nothing but edges. B and C have an edge between them, A and B, A and C and so on. So all these are edges. Now that brings us to our last term which we have to see today, and that term is height of a node. Now what do we mean by height of a node? The height of a node is the number of edges on the longest path between that node and a leaf. Now let us understand this a bit. Now suppose we have to calculate the height of this node here, that is C. Then we have to check the longest path between that node and a leaf. So the leaf here we have F and J. The path between C and F is 1. From C to J we have 1 plus 1, that is 2. The longest path length is of 2. So the height of the node C becomes 2. Now suppose we have to calculate the height of the root node, that is A. Then we have to check the longest path from A to all the leaves. And we have D as a leaf, H, I, F and J as leaves. So from A to D we have a path length of 2. From A to H we have a path length of 3. Same with I to 3. So out of these, as we can see, 3 is the longest path. So height of A becomes 3. So that was all for this video. You can like, share and support my videos on Patreon. In next video we will talk about binary search trees. See you in the next one.